Some more numbers that we're going to need in counting problems are called multinomial coefficients. Maybe I shouldn't say more numbers because we've actually seen these numbers already. You'll probably recognize them at some point in the video. Let's consider two different counting problems to start off with. Question 1. In how many ways can we break 6 people into 3 teams of size 2? And the related question, what if we label the teams? Let's call this question 2. What if we label the teams Team A, Team B, Team C? So in question 1, 2, 4, 1, 3, 5, 6. So these vertical lines are supposed to tell us that these 2 people are on the same team, those 2 people are on the same team, those 2 people are on the same team. This is equal to 5, 6, 2, 4, 1, 3. Because all we care about is who's on a team with whom. But in question 2, these are not the same. 2, 4 on team A, 1, 3 on team B, 5, 6 on team C is not the same as 5, 6 on team A, 1, 3 on team B, and 2, 4 on team B, and 1, 3 on team C. The question 2 is actually the easier question, so let's answer that one first. So to answer it, we'll line up the 6 people in 6 factorial ways. For example, say 2, 4, 1, 3, 5, 6, and then we'll draw vertical lines to create the teams. So for example, 2, 4, vertical line, 1, 3, vertical line, 5, 6. Now, we have to realize that if we'd written 4 before 2, that would actually be the same team of 2 people. Person 2 and person 4 together. So then we divide by 2 times 2 times 2 to correct for the overcounting of 2, 4 and 4, 2 really being different permutations when we say 6 factorial. Similarly, 1, 3 and 3, 1, which we count differently in permutations, really should count as the same, because if person 1 is on the team with person 3, it's the same thing as person 3 being on the team with person 1. So we have 6 factorial divided by 2 times 2 times 2. Running out of space here, so I will just put a colon here in the answer. Etc. 6 factorial divided by 2 times 2 times 2. Alright, now let's answer question 1, which actually starts just the same as question 2. We want to break 6 people into 3 teams of size 2. So we can write out the 6 factorial permutations of the 6 people and then draw vertical lines to say who's on which team. But we want to count this permutation the same as that permutation. Because if 2 and 4 are together, we don't have a team A, a team B, a team C anymore. We just have 3 teams. So if we want to break 6 people into 3 groups of 2, we have to correct for overcounting of these 3 blocks of 2 numbers permuted in 6 different ways. So we'll start the same way. So permutation like 2, 4, 1, 3, 5, 6 becomes 2, 4 vertical line, 1, 3 vertical line, 5, 6. But we want to count these 2 arrangements of the 6 people into 3 teams as the same. So we can do this in 6 factorial over 2 times 2 times 2 ways. But now we are overcounting. By a factor of 6. Because the 3 teams say 1, 3, 2, 4, and 5, 6 can be permuted in 3 factorial, which is 6 ways. Which result in the same arrangement of teams. The same arrangement of the 6 people into 3 teams. So that means that there are 6 factorial over 2 times 2 times 2 times 6 ways to form the teams. I guess we could cancel a 6 from the 6 factorial with that 6 and just have 5 factorial over 2 times 2 times 2. Alright, now let me state the general formula that tells us how to answer questions like this. Now, unfortunately, the general formula is stated incorrectly in the book on pages 9 and 10. So Ross states what we called question 1, but then he gives the answer to question 2. Let me say he poses question 1. But then he answers question 2. Not because he doesn't understand the difference. You can see he understands the difference. If you look at his example 5b and 5c, he actually compares and contrasts the two questions. But unfortunately in the formula he didn't choose his words carefully enough and ended up answering a different question than what he posed. So let me state it correctly. So if we're given numbers a1 through ar, which are non-negative integers, and they add up to n, then let's let n over these integers subtracted by commas and inside parentheses. I don't know a nice way to say this. I guess you could call it n choose a1, a2, a3 up to ar. But people, I've never heard people say it out loud. I don't know the right way to say that. But so let's let this notation be the number of ways to break a set of n objects I'll say a set of size n into subsets labeled 1 through r, and this is what he forgot to say. Where subset I has AI elements. So that's a definition for this notation. And if we define it that way, don't forget to say labeled 1 through r, then n choose a1 through ar equals n factorial over the product of all these factorials. a1 factorial, a2 factorial, etc. up to ar factorial. So now let's do another example. So let's say 10 people who are planning a party. Need 3 to cook, 3 to serve food, and 4 to clean. We'll ask in how many ways can they do this? The answer is 10 choose 3, 3, 4, which again is equal to 10 factorial over 3 factorial, 3 factorial, 4 factorial. So we're basically breaking the 10 people into 3 teams, labeled the cooking team, the serving team, and the cleaning team. So that's why the answer is 10 factorial over 3 factorial, 3 factorial, 4 factorial, because the subsets are labeled 1 through 3 in this case. And then the variation if the 10 people want to break into teams of sizes 3 and 3, 4 to play a game. Now the teams are not labeled anymore. We don't have a team A, team B, and team C. Just have 3 teams, 3 people, 3 people, and 4 people. Then the number of ways to do this is 10 choose 3, 3, 4 times 1 over 2. Because 10 choose 3, 3, 4 really means put 3 people on team A, 3 people on team B, and count that differently as putting these 3 people on team A and those 3 people on team B. But if we don't want to count those as different, we're just breaking the people into 3 groups and not naming the groups. We divide by 2 to account for the overcounting of calling these 3 people team A and those 3 people team B different from these 3 people on team A and those 3 people on team B. So this 2 corrects for the overcounting of, let's say, 0, 1, 2. Let's say the people are 0 through 9. 3, 4, 5, 6, 7, 8, 9, and 3, 4, 5, 0, 1, 2, 6, 7, 8, 9. The overcounting of those 2 things being counted separately. Alright, let me erase this different variation, and I want to look at the first question from 2 more points of view. So first of all, in how many ways can we rearrange the word 1, 1, 1, 2, 2, 2, 3, 3, 3, 3? So we've done this before, and the answer is there's 10 letters there, 10 factorial. Divide by 3 factorial to correct for overcounting of the 3 factorial permutations of the ones that don't really make a difference. And another 3 factorial to correct for overcounting of the 3 permutations of the 2's that don't make a difference. And divide by 4 factorial to correct for overcounting of the 4 factorial permutations of the 3's that don't make a difference. Well, that's the same answer to this question, which is why I said that we've seen these numbers before. So why is this the same answer? So this is the same answer as above. because we have 10, let's say, spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which are going to hold these numbers. 3 of them are going to be on team 1, which is just like being on the cooking team. Three will be on team 2, which is just like being on the serving team. And 4 will be on team 3. Which is just like being on the cleaning team. So every assignment of 3 people to cook, 3 people to serve, and 4 people to clean really corresponds to an arrangement of the word 1, 1, 1, 2, 2, 2, 3, 3, 3, 3. If each of these spaces, 1 through 10 or 0 through 9, counts as a person. Alright, so it's really just another way of looking at the same problem, looking at as rearrangements of a word rather than as assigning people to 3 labeled teams. Now let's look at this problem from a third point of view. So let's ask, what is the coefficient of x1 cubed, x2 cubed, x3 to the 4th in x1 plus x2 plus x3 to the 10th? So if we take this multinomial expression, we've got this multinomial raised to the 10th power, what is the coefficient of this monomial? So the answer is, it is when we multiply this out, write it 10 times next to each other, from every factor we're going to be choosing an x1 or an x2 or an x3. So we're basically going to get a bunch of monomials, each of them 10 variables long, where we chose one from this factor, one from that factor, one from the next factor. So it is the number of rearrangements of x1, 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 x2, 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 x3, 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 which is basically the number of rearrangements of 1, 1, 1, 2, 2, 2, 3, 3, 3, 3. So 10 choose 3, 3, 4. And the fact that this coefficient comes up when we raise a multinomial expression to a power is where we get the name multinomial coefficient from. The end.